Okay. So should I start or should I wait? I start. Okay. Yeah, so I'm gonna present like kind of a quick, hopefully that's due to the tight deadline. I'm gonna present really quick, kind of a summary of what I have been doing during these 3 years in our university. And then this title is hard to be done, to be honest, because the initial title I had for my PhD thesis was not really what I actually end up doing. But let's go for it. So first, this is the outline that I'm going to follow. I'm going to try to provide a bit of a background on the problem that we are trying to address during this presentation and during this work. Then some research goals and questions. Next section would be most focused on methodology. So basically, I will show how we present two different methods to create radio maps of the environment based on large scale massive MIMO. I will go into details later on. And then some application of results regarding all these methods that we that we will present in a couple of minutes. I'm wrapping up with some conclusions. So first, the first background check is what is a large intelligent surface? So I want to point out that I'm working in large intelligent surface, not in reconfigurable intelligent surface, because sometimes I usually confuse these two terms. This mainly means a really huge array beyond massive MIMO array, which is a really large, has a really large aperture, a high amount of antenna elements that are tightly or closely spaced. So the idea is this kind of surface give a hint or give an idea. It's almost a continuous electromagnetic surface. So basically, the main advantage of these systems is that they can be really easy to integrate into the environment. We can place an array into the wall, maybe into the ceiling. We will discuss later on about that. And in the literature, there is a lot of studies regarding its communication capabilities, because we can get really high fine-grained beamforming and high spectral efficiency due to its features. But here in this work, we are focusing mainly in exploiting this system for sensing. So here we have kind of a really exemplary thing. So let's imagine that we have an access point that is trying to communicate with a user. So this access point is mainly trying to send the signal to the user, but there is a blockage in the line of sight. So the idea is, in our work, is that we will use the, let's say, signals occurring in the environment, so the reflections in the scatterers, walls, everything, in order to extract some information of what's going on. Once we have that, we should be able to optimize or improve the communication towards the end user in this case. So yeah, this is a bit, again, wrapping up the same I have just said. So due to the communication capabilities are well proven, so we focused on sensing. Concretely, we try to address this by developing radio map methods to describe the environment. So here are like the problem and research goals that we try to address during this work. So the main goal is we try to explore beyond massive MIMO sensing capabilities for the integration between sensing and comms, using mainly large intelligent surface. And then the specific research goals would be like, which methods can we actually develop for radio sensing and create radio maps of the environment? And if we can compare this large intelligent surface with other radio sensing method in order to see what is the trade-off that we can encounter because of that. Then the main research question to ask is what are the benefits of using use LIS for wireless sensing? And the specific research question that we try to address during all this time is what are the best methods to do so? What is the impact on the least parameters in the sensing performance? And what are the applications that we can have out of it? So here, it is like a really schematic representation of what we meant by sensing. So let's imagine that we have some signals occurring in the environment. Here, for example, these women are using their smartphone. We could think of routers or smartphones, or laptops and so on. So these signals are traveling through the air, into obstacles, other people, and so on. And we can measure the reflections in an LIS that we deploy, for example, in the wall in this case. So we can see that we can have a kind of a pattern that is affected or governed, let's say, but what's going on in the environment. So this is the main idea that we want to exploit. And for that, we propose two types of, or two ways to do a radio maps based sensing with LIS. So let's say the first one is what we call holographic sensing. So let's imagine that we have deployed an LIS with n antenna elements in the wall. And then in order to make it cheap, because in this case it's a really huge array, we are just basing on incoherent detectors. So we are just detecting the envelope, mainly the power, the signal power. And then the large of antenna element, the higher number of antenna elements that we have lead us to have a really accurate image or representation of the environment. So this hopefully should close the gap between computer vision and image processing in a wireless sensing kind of field, so to say. So here we have two exemplary radio maps using holographic sensing. The first one corresponds to a really line of sight scenario. It's not that descriptive, but what we want to show is the comparison with what we say denominated as industrial scenario. So we deploy an LIS in a wall in an industrial scenario. And then in this scenario, there is some scatter. There is some walls, there is some columns, there is some obstacles. And then we have an industrial robot that is transmitting constantly a sensing signal. And so the LIS is just measuring. So what we can see here is that the holographic image, or this is like the received power in the entire LIS deployed in the wall, is kind of capturing some shapes or some, let's say, information about the environment. It's kind of showing that we have some scatterers between the transmitter and the receiver, in this case, the LIS. So here we are kind of giving a hint, let's say, of what's going on in the environment. This is the goal. Then we propose a different radio map generation or match filter, different sensing method with LIS, which we denominate as match filter sensing. So again, we have our LIS, but instead, this time we deploy it in the ceiling. And this LIS, we take advantage of the communication signals occurring again, as previously. But we have to take into account that we are in a near field condition because we have a really huge array in a really short distance with respect to transmitter and receiver. So we take into account that into the modeling. I will go into that later on. But mainly what we can see here is that the left-hand side, or the first figure, we have the spherical wave match filter. So mainly like how the steering vector look like from the LIS viewpoint. Then if we convolve this spherical wave pattern with the received signal, complex received signal, we can obtain something like the image in the middle. So what we can see here is that we have a transmitter, which is clearly denoted here because it's the highest peak in the map. And then some kind of circle shapes. I don't know if they are well shown in the projector, but there are some kind of circular shapes that correspond to a scatter. These scatterers are shown in the map, also some reflections from the walls and so on, are shown in the map because they are as virtual sources. So mainly the reflections are in all the different points along this scatter are acting as virtual sources, and that's why we capture them somehow in the map. Then here we have another really simple exemplary scenario. So here there is no mainly scatter, it's just the walls and of course the ground. But mainly what we have is just a target participant. So this participant moves around, and we can see here that if just by measuring the reflection on the off of the body of this participant, we are able to obtain a map that kind of is giving us a hint of where this passive user is, where is the human in this case. So let's get a bit into the modeling. So these are the two system models that we use mainly. So for the holographic sensing is the simplest one. As I said, we measure the received signal power. We have our LIS with the A antenna elements. And we assume that we have in this industrial setup that I was mentioning, kind of just a robot transmitting a sensing signal. And this is the received signal that we obtain. And finally, we are using incoherent detectors, so we just measure the power. So basically there we are representing the power at the I antenna elements. And then the match filter sensing tries to take advantage of multiple active devices in the scenario. So I have multiple laptops, multiple smartphones, and so on. And they are transmitting signals. So we have at the end, the receiver side at the LIS, the summation of all these active elements. Basically, as I was saying before, we have to account for near field. So we know that the near field is proportional to this expression. This is what we use to design the match filter that I was mentioning previously. And this is what we use to convolve the received signal in order to obtain the previous map that I showed before. So just to bit more of detail of how we model the received signal. So basically, we resort on ray tracing because we wanted to provide a kind of accurate modeling of the propagation environment. So in order to do that, what we do is that the received signal, this Y that we had before, is the superposition of all the ray paths in the reflections and all the active elements in the scenario is the superposition of the complex electric field. Then we assume some isotropic antennas, and that's why we have this following expression. So this is the free space impedance, is the impedance that we assume 1, just for the sake of simplicity. So here is our received signal that is more or less the superposition of all the ray paths and active elements, as I said. And then, so to leverage the sensing performance, we define a signal-to-noise ratio, which is mainly the average along all the antenna elements of the LIS to provide some hints of how it works in different noisy conditions. Then I will go really briefly into the application and results. So mainly for the holographic sensing, which is the power-based, we have two main applications that we try. First is the supervised anomalous route detection in an industrial setting. And second one is the unsupervised that we'll develop in the next slide. But mainly what we have is here is the scenario that we were simulating in the ray tracing. So this red kind of cylinder represents the robot. On top of this robot, it has a transmitter. And this robot is going to be moving either in a parallel way to the LIS or in a normal way, direction with respect to the LIS, as we can see here. So mainly what we're going to try to do is a really simple problem, try to determine if this robot deviated or not by, let's say, leveraging several parameters of the LIS and see how it impacts on the performance. And then for the supervised, it would be the same, but it would be just in an unsupervised fashion. I will develop later on. And then for the match filter sensing, which is the other method that we propose, we have a kind of 3 applications. So the first one is active and passive indoor user localization. It's going to be something like this. So this little square corresponding to the modeling of some humans with the skin parameters for reflection of the signals and then some scatter. I would also develop later on, but we will see how we get this kind of result that is able to localize passive users in a passive manner. Also, we do a comparison against a millimeter wave radar in order to show what is the trade-off between using an LIS, which is a system for communication, and comparing with a system that is designed for sensing, which is this millimeter wave radar. And also then the last application that we also track is a floor plan reconstruction based on radio signals. So we have these devices transmitting. This, for example, the arbitrary floor plan. And what we have here is some measurements of the signal. So if I measure the signal just once, I don't get something really visible. But it's true that if I assume that the coherent time is long enough, I can sample the signal more times, and I should be able to get a more accurate radio map of the environment that is trying to represent this floor plan. Then our goal would be translating this floor plan, this radio map to the target floor plan that we have there. So for the supervised anomalous route detection, what we do is we measure the signal, we map it into a 8-bit grayscale image. As we don't want to spend a lot of time sampling the signal multiple times along the route of the generated data set, we rely on transfer learning in order to be able to reduce the amount of data that we need for training, where we concretely reduce the parameters of the VGG19 and to perform feature extraction. And then really simple, in a really simple fashion, we will try to classify, in this case, in a supervised manner with a super vector machine, these features correspond to a correct route or incorrect or anomalous route. So here are like the first hints that we wanted to show. So these 3 plots are showing different configurations of LIS parameters. First one corresponds to noise averaging. So basically this extra sampling. If we receive 1,000 samples and we average the received signal, at the end of the day, we are reducing the noise variant contribution. So we are improving the sensing performance. So this is what we are trying to show in this one. So if we start with an average, sorry, if we start with the no average, we have a reduced drop even in the highest scenario. Then if we start with the averaging of the received signal, we kind of improve the result very much. Then here, the next one is what is the impact of the spacing between antenna elements. So what we see here is that the lower the spacing between antennas, the better the sensing performance, the better we are able to detect. So this is mainly showing that the quick variations along of the signal along the surface is providing meaningful information because it's actually impacting quite much into the performance. Finally, another, let's say, insight what we wanted to provide is we fixed the spacing of as lambda over 2, so the best case here. And we just changed the number of antenna elements. So we increased the aperture of the LIS. And again, we see that the result is that the higher or the higher amount of antenna elements, the higher resolution image, the better detection. But then it's more interesting, I think, going to the unsupervised anomalous route detection. So mainly the backbone, let's say, is completely the same as before. But what we do now is that instead of using a super vector machine, which was a bit of an artificial problem because we had anomalous and correct points for training, we just rely now in sampling along the correct route. Basically, we use this output feature that we had before into a local outlier factor. So local outlier factor is basically a clustering algorithm that compares local density. So it compares the clusters in terms of density of points nearby. So that's why if we have a close deviation, it should be able to detect it anyway, because it's comparing that outlier should be really less in a really dense area than the correct route that learned during the training. Also, another kind of improvement that we included is that, okay, as we are using kind of image-based approach, we can try to take a look into computer vision. What do they do to enhance super resolution and to improve the quality of the images? So here we have kind of a really simple idea, but effective, as we will see later on. So we use a denoise autoencoder as an image super resolution. What we do is that we get, let's say, measurements from a really small LIS, so small in terms of number of antennas, so 32 times 32 in a really low SNR condition, minus 10 dB, for instance. So this is the condition of one snapshot that we have. And then we try to augment that resolution into 128 times 128 with higher SNR condition. So at the end, what we have is two images of the same event, but one is way more, it has a higher resolution, so it should be better. Then what we try to do here is that the encoder learns this mapping from a lower or harder condition towards a higher and better condition. So here we are kind of doing a mapping from a lower resolution image to a higher resolution image. And these are, again, some results regarding that. So first one, we take a look into the extra sampling, as we said before, but we also take a look into the fact that averaging, as we said before, is useful, because if we use this, let's say, sample several times and feed all of that into the neural network, into the feature extractor, it's not that convenient. We have really good results, you can see here. Also, we see that we are kind of going lower in this line. But so here we have, if we use the direct guidance, it's not providing any insight or any improvement. However, if we start averaging, as we said before, we reduce the noise contribution and we increase the performance. Here we have similar insight as we had before in the supervised case. But yeah, so mainly the close separation is always better into the sensing performance. We test deviations of normal trajectory and parallel trajectory, as I pointed out in the beginning. Here is again the kind of same conclusion for the aperture, so I will skip it, but this is a more interesting part, I think. So here, what we do is, okay, let's try to actually evaluate how good using a map of an environment is. For that, what we do is first, we design an hypothesis test as a benchmark. So in this hypothesis test, we have a lot of prior information. We know that the noise is Gaussian. We know that we model the signal as a recent distributed. So let's say that we have some prior information that we neglect completely in the machine learning approach. So that's why we compare against the benchmark, the hypothesis test. And then we also evaluate like how well it generalizes to another scenario. So here in the first plot, we have this comparison. As we can see, the hypothesis test is optimal, so it's normal that it's going to be a benchmarking and being the best, beating our solution. But the main takeaway here is that even for an scenario of 2 dB or even 0 dB, in some of the cases, we have a really close to the benchmarks performance in the sense. Also, another interesting point to highlight is that as we are using this autoencoder for augmenting the image resolution, we have a behavior that is contrary to the traditional wireless sensing. Because if we see here, the 10 centimeter deviation works better than the 50 centimeter deviation. This is, in principle, might seem wrong, but it's not actually the case. It's because the closer the deviation is, the more similar to the training set that was just trained in correct position. So that's why when we have a smaller deviation, we are able to detect better. So this is kind of embed advantage of using a radio maps sensing strategy with this approach. And also, just kind of a highlight, as I said before, we are kind of working into low SNR scenarios. So 2 dB is still a good result, 0 dB for some of them is kind of acceptable. And then the last, the last figure, what we are trying to show is, okay, so how it is affecting to the performance that we change completely the mark. So the red one corresponds to this. First one corresponds to the static scenario, so mainly the same scenario that we had before, the same plot basically. Then what we do is what happened in the performance if we change the scenario, which is this square. So we can see that up to 4 dB, we are still able to accurately determine the anomaly. But it's true that, no, up to 2, sorry. But it's true that up to around 0 and lower, this is clearly flagging that we need to retrain because the scenario changed too much from what we expected in the training. But it was just an evaluation of the generalization, so to say. Then the next one I want to go into is, okay, I don't know if I take it too much time. But okay, so this is like active and passive interlocalization. So we have the radial map. This is the other method that we mentioned in the beginning. We do some kind of image processing into the radial map. So the first step is we do a k-means clustering of the pixel value, because we can see that we have mainly 2 different range of values in the pixel domain in the image. So we obtain this cluster radial map. Then what we do is by combining different active devices and doing a filtering, because in the filtering we remove the transmitter, as you can see there. We can obtain like a map that is just describing the static parts of the scenario. This is the second step. Then the next step is, okay, once we have how the static scenario looks like, let's measure like the signals that are occurring in the environment, and we have a negative map. Negative map in the sense that now the obstacles are represented as black, and the background, let's say, is represented as white. So having that, what we can do is that we can perform an OR operation between this store map in the LIS and this new measure map, such that we remove the static parts of the scenario and we just let like the events that were new, so mainly the targets in this case. Finally, this is kind of the scenario we were simulating and an example. So once we have this part, we applied component labeling. So maybe it's a kind of a window algorithm to make the union, let's say, between the shapes in order to determine that this corresponds to all the passive users. And these are some results. So the first type corresponds to the detection as a benchmark is the detection of the active user, so the active transmitter. This is really simple because as we had in the map, it's just looking for the peak, as we saw. So it's kind of showing that for active detection in a 0 dB condition, we have a really good accuracy in position, let's say. Then, which is more interesting, is this passive localization of target. So mainly we test the effects of augmenting the number of random active devices in the scenario. So we can see that the trend is that if we augment the number of active devices, we increase the detection performance. So we are able to detect more accurately the passive, the human, let's say, all the people that were there. And yeah, we see that we cannot have an acceptable error in terms of localization just in a passive fashion. Here is just for illustration purposes, kind of a plot showing the localization of passive users. The ground corresponds to the blue dots, and the red dots are the prediction. Then I will be really brief here. So it's just in this work that we tried is using the match filter radio map. We try to compare to the radar, just in order to show that how good or how, let's say, how worse, better said, how worse the LIS is in comparison with against that radar, being not a dedicated device for that. So here we have our participant, which left the room, by the way. And he was walking around here. So we obtained some ground truth and with his radar. So this is the experimental setup, and the LIS is in the simulated environment that we proposed. So here is kind of the system model for both things. I will be really quick. So first one is the one that my colleague presented in the morning. So we obtain some contracts and we process them in order to go to the bounding box around the user, the target user. And here it is just based on the radio map as we saw before. So we are going to try to compare maybe these two systems. So these are is the insight that we obtain. So we measure maybe two metrics. The intersection over union and the distance error. Intersection over union is mainly just the area of overlap of the predicted bounding box with respect to the ground truth. And the distance error is just the center of the bounding box. So we can see here what we expected and somehow. So the radar is outperforms in terms of localization performance to the LIS. But the important or the takeaway message here is that it's just a 7 centimeter different error. With all the advantages that this system, LIS, is really proved to be working and really good for communication capabilities, something that the radar cannot do. So mainly we are showing that LIS can have an almost accuracy in positioning as radar would have. And we can integrate both of the functionalities into the same device. And just to finish, I should be quick. Yes. So this is like an other application. So we try to translate the radio map into a floor plan of the environment. So we compare mainly three methods. The least square method, although super naive, is what the people used in the literature a lot. So that's why we included to compare. The unit is basically this encoder autoencoder with a skip connections that we also try to do to translate from radio map to floor plan. And finally, the one that we, let's say, proposed and that we focused on, which is the conditional GAN with matching loss. So what we mean with matching loss is that we have this extra term that mainly minimize the distance between the in-between features when the input is the fake generated sample or the real generated sample. So this is what we mainly want to show. And here we have kind of a visual exemplary reconstruction. So we can see that kind of we have some accurate reconstruction from the unit and the conditional GAN, and really bad for the linear that was proposed in the literature mainly. And so here we have kind of quantified these results. So first part is the evaluation using more or less samples with the averaging that we always mention. And so we can see that the conditional GAN outperforms all of the rest. And here is mainly to have a kind of a clue of the distance error between the floor plan, ground truth floor plan, and predicted floor plan. So we can see that the results are kind of okay. I don't want to. I mean, I'm a bit extra out of time. So yeah, so these are the conclusions. And to wrap up, so large intelligence surface, as I said, is also useful for radio sensing. That's what we are trying to show here. Also, all of its parameters influentiate into the sensing performance. We can see that also performs kind of closely to the radar, which is something that is good. Then we aim to say that the radio map can bridge the gap between computer vision and wireless sensing. Yeah, and finally, large intelligence surfaces are maybe always mentioned as like one of the key enablers for future 6G. So we kind of try to show that it might have some high application potential. And this is just mainly some research outcome, kind of a summary of what I have been doing for this year. So mainly these are my published works, and these are two other published works, but let's say, I would say extra topics because they are not specifically about LIS, but the collaboration with the rest of PSRs. Yeah, and that's all I have. Yeah.
The slide 21. You said here
this one.
this radar one was a setup.
Yeah.
Test bed, and the other one was simulation.
Yeah.
How do you compare these two?
Yeah. Basically, first, because that's why we try to do a really simple setup. As you see, the setup is mainly a line of sight with the radar and in a circular area. So mainly what we do is that we simulate in the ray tracing exactly the same. So the same area, the same distance between LIS and target and target in this case. So similar to the experimental setup, we mimic that into the simulation in order to do a fair compare.
I have two, but let me use one. We have an situation now. We have the heights of the element that you're sensing. Actually, LIS, can we see it's gonna work on video?
Okay. With respect, let's say first, with respect to the height, it doesn't really matter, but let me show you maybe with one of the plots. Let me, what is it? Yeah, maybe with this one. Yeah, maybe with this one that, oops, sorry, this one that we have here. So mainly what we do to design the match filter is assuming that the distance from the transmitter, although it's not correct, but to the transmitter to the receiver is as if the transmitter was in the ground. So it's basically the distance that we are assuming in the set coordinate is from ground to ceiling. At the end of the day, what it happens with that is that we can see this as a camera. So when you focus more, you have a higher resolution, and when you focus less, it's a bit blurry, but still you see something. So this is what we did here. So we put it in the ground, the distance, so to say, with respect to the ceiling. So I'm sure that if I calibrate the match filter, knowing the height of my obstacle, I'm gonna have a way better representation of it. But that is inconvenient because then I have to assume that I know all the height of the tables or whatever I'm modeling. So that's why I did this way. So I don't know if that replies to your.
Yeah, so follow up on that. What if you did like several layers? So for instance, if you have one layer, 7 million meters or whatever, would that be marginal difference? And put it into that for like a 3D?
Yeah. Actually, I don't know if you remember, I showed you a thing in Albor, but in Albor I tried this. It's mainly a layer, like layer by layer, so moving the height of it and compute, and you can get kind of a 3D representation. I don't have results here, but I think I showed you, right? So you can have kind of a 3D estimation instead of 2D as here. If you move if you change this distance. Yeah, can put it.
You're using your pen.
Yeah.
Okay.
How's this understanding? So this LIS on this use case scenario, where is it? Is it
Ceiling.
covering the whole?
Yeah. It's covering the whole. That's something that it's easy to criticize, I would say. But right now it's that way. What we also tried, or we wanted to try, to do kind of patches, because it's true that having the aperture covering the entire ceiling is a bit unrealistic or arguable, let's say. But yeah, this was kind of a proof of concept that we can do that. So that's why we did this way. It's a simplistic way of seeing it. But yeah, if the concern is too big, I also agree. Yeah.
So, this device with some millimeter wave?
Yeah, sorry, I forgot to mention. The radar is operating in 70. The LIS in 3.5 gigahertz.
Sorry?
3.5 gigahertz, because we need reflection. So if we increase too much in frequency, we lose we have too much line of sight. Yeah, okay. Oh, this is not like. Yeah.
You close this one, then the other one is yours.
For the sake of it, no?
It's a nice experience.
Yeah. First time using it, so yeah, why not? So I guess everybody knows me, so my name is Roberto. And today we'll be talking about subspace clustering on massive MIMO. And it's basically a compilation of a couple of papers that we made throughout my thesis or throughout my PhD so far. And yeah, I'll try to be short. This is an outline of the presentation. So I try to motivate a little bit, and then we go into some works. So the first thing that we were thinking is we want to work on massive MIMO, and to give you some intuition why. In the beginning, what people wanted to do or tried to do was to do orthogonal multiple access. That was 3G. In 4G, people start to realize that it's nice to share resource. And then in massive MIMO, what people start to do was to increase the number of antennas to try to serve the maximum number of users. The problem with that is that, I mean, we have limited number of space, right? So you can't just put all base stations, all access points everywhere. Then what happens is that if you have limited number of antennas, at a certain point, it might be the case that you have more users to serve the number of antennas, and that's more or less a problem. And what happens that apart from that, some of these other solutions usually rely on optimizations or, for instance, power allocation, antenna selection, user clustering, or pilot allocation, as someone mentioned before. But the problem is that these optimizations might take longer when you increase the number of elements. So if you increase the number of antennas, the number of users, or the number of base stations, meaning those solutions are often unfeasible due to computational time, storage, parameterization, iterations. So what we want to do here in this work is to try to cluster some users or try to find some similarity among those users and try to perform those optimizations in a cluster or grouping-based solutions. So we focus mainly in the clustering of the users, actually only the clustering of the users. And then throughout here, I'll be talking about some of the works. So to give you some illustration, basically the idea that we have a base station and would like to cluster these user equipments or the users according to the CSI into different groups. And the way we want to do it, we want to check what is the similarity between these users. And we have basically proposed 2 ways and one user case study to motivate the work. So the case study that we first analyzed, I think 2 years ago or so, in the beginning of the PhD, it's basically what is the optimal clustering scheme? I mean, is it better to try to use the position of the user? Is it better to try to use the CSI? Is it better to try to use other features? We went with the CSI because the easiest one to acquire, not the easiest one, but I mean, the one that we found it was good. And then we decided to do, okay, what do we do now? We can beamform on a group level, so there's 2-tier precoding stuff, and we want to perform some successful interference cancellation. That was 2 years ago, so trying to do some normal scheme. So in short, we cluster the users, and then within each group, we perform some successive interference cancellation. That's some case study that we want to analyze how the clustering of the users would affect the rate or the spectral efficiency or so on.
So, sorry, I don't understand.
Sure.
The cluster must physically close one another?
Not necessarily. That the CSI is physically close, which usually relates to the position,
So
but
which have similar challenge.
yeah, but if you are in the multipath scenario, that not really is the case. I mean, it could be that there is some reflection, and due to the reflections,
So it's important you suggest to apply successive interference translation among users that have similar challenge.
yes,
Then usually
it's the opposite. Yes, but you can do this with power. Yeah, yeah. So you can do this with powers.
Right.
I mean, yeah. So it's normal. No, yeah. Yes, that's it.
Yeah.
So the main point here is that we are mostly focused on the case where the number of users is larger than the number of antennas. So you cannot multiplex to all the users. That's the motivation of the work since the beginning. So what we try first, it's a Excel sheet search. So we try all the possible scenarios. As someone told before, that's a very computational expensive. But in short, what we do, we divide users, single antennas users into some groups. We set that the number, the SNR for each group should be fixed. We define a beamforming, and then we try to find out what is the effect of grouping users in one way or another way. Again, that's just a case study, just to see what would be the effect of doing so. And what we found out long time ago is that they clearly cluster the users in different scenarios. It affects the spectral efficiency or the rate, or however you want to put it. So in short here, what we have is 3 examples of clustering. So we have one, which is the optimal one. So if you try to cluster the users in colors, so each color represents a different group. So if you cluster all the users according to some specific measure that you want, it's undefined here because you try all of them. You find one specific cluster which is the best. And what is perhaps a bit more important is that not only it's the best because it's close located, but it's because sometimes the echo or the noise from the within the group, it's large, or the noise among different groups, it's large. So there is a trade-off in between how you define the group itself and how you define the groups nearby. And that's the whole motivation of why we are trying to cluster. And the question is now, how do we choose the optimal group? Because if we perform this, search all the possible groups, that's impossible. After a couple of iterations, it becomes too large. So we thought of a very simple solution at the time. And we thought of doing spectral clustering because it's well known in the literature. There are a bunch of nice properties in the clustering. So we thought, okay, why not? And then we searched a little bit in the literature. And one of the important questions is in spectral clustering, it's how to choose a kernel function. Because the idea in the spectral clustering is that if you have some set of points in some dimension, it might be useful for you to apply some kernel function or transformation function into the data set, transform it in a different dimension, and cluster in this different dimension. Well, the question here is which function to use. I mean, you could again try set of different functions to perform this clustering, but there are other ideas in the literature. And one of these ideas is to try to analyze the spectral behavior or how good this function behaves. So in short, I could try to analyze if I choose different functions, what is the best function that fits in an asymptotic behavior? So I mean, I say, okay, I have this function, I have this set of data, what would be the expected behavior without actually calculating the similarity itself. And to do so, we do an asymptotic behavior of the data set of the kernel functions. So for instance, here we have 2 different functions. We have a kernel function, a sine function, sorry, and we have another radio-based function. And the idea here is that without actually performing the spectral clustering, we more or less analyze what is the adjacent relationship between the points in the graph, because I forgot to mention, but the whole idea of this clustering is to measure what is the similarity in these points here. So basically, there is a close relationship between the kernel function that I use, the adjacent matrix in this graph. So if the eigenvalue of the whole adjacent matrix or the Laplacian adjacent matrix, if the first or the second one is large or small, there is a way to cluster these users. Yeah, so the dimension is the user is it's a one antenna user, and the base station, it's a multiple antenna. So it's a MISO scenario. So yeah, it's a MISO. So what do you mean by parameters?
So how do you define this?
So how you define the adjacency? It's basically you perform a multiplication. So you perform some similarity between 2 points. So if xi is a point, xj is a point, you perform some cosine similarity or something.
What are the?
What do you mean by?
Find the mistake side, what is the side?
Ah, it's just a right now it's a Gaussian variable. It's a random Gaussian variable. Complex. Yeah, it's supposed to be the channel. It's supposed to be the channel, but it's a random Gaussian variable, complex random Gaussian variable, which is a problem in the future. That's why it motivates the next work. So the point here is that what we were trying to do at the time was trying to analyze how to cluster these users, and one way to do so is to choose this complex function, the Kernel function. But the problem is that, as I just mentioned, it worked at the time on MISO. So because it was only focused on MISO and we wanted to work on MIMO, so multiple users or users with multiple antennas, it's not really what we wanted. So we went a step back and revised the problem. And what we had at the time is that the spectral clustering only works first if you had a large number of observations. So if you had a large number of antennas, for instance, it's not really extendable for MIMO, meaning if you had one user with several antennas, it wouldn't be extendable. And again, the number of users had to be, the number of antennas in the user had to be the same, meaning one. What we need is a robust classification scheme that's capable of doing both with large and small number of observations, that consider multipaths, that go to what Andrea was saying, applicable in MIMO, and that's capable of clustering users with different set of antennas. And what we propose is actually a hierarchical clustering mechanism, because if you have a hierarchical clustering, you could do with large number of observations or a small number of observations, because you're basically doing pairwise comparisons. No explanation of, because then we can apply for massive MIMO, and subspace because you can apply for multipath. So to give an idea of more or less what is the system model, perhaps I skip a bit, because that's the entry. So it's basically the chain of the matrix. We have a Kernel model. We have a base station with some covariance matrix. And what we want to do here is to analyze what is the similarity between two channels. So if two channels are similar, it's very likely that in the MIMO scenario, they have the same distribution. And if they have the same distribution, basically means that they are from the same covariance matrix. So we can do this as a hypothesis test. Basically, in the null hypothesis, we have the scenario where this is true. In the alternative hypothesis, we have the scenario where the covariance matrix are different. The problem is how to do this in real world applications, or how to do it when you don't have access to the covariance matrix.
Something equal.
Oh, then it could be like proportional. Yeah, I mean, because yeah, it could be proportional. But in the scenario, we assume that they're equal. Meaning, if they're equal, basically the idea is that they come from the same direction, but it could be proportional, to be honest. Yeah, so the idea of the hierarchical clustering is that provides a easy way to perform comparison among different users. And basically the idea is that we are interested on clustering users that have similar angle of arrival. But in the multipath case, that again reflects to users that have similar subspace. So if I have two CSIs, I can try to analyze a projection matrix that's a point in some manifold, in this case the Glasmanian manifold, and I can try to analyze the cosine similarity between those two matrices. But again, this manifold, one way to do it, it's with this lambda, which is basically the eigenvalue of this product. If you normalize it, we have some similarity matrix, some similarity value. That's what we are interested in. And basically the idea is, okay, if I have the similarity between two groups, maybe in the middle of it, if I have the similarity between two groups, I decide, should I merge the two groups? Should I not merge the two groups? So with that, we can perform a hierarchical cluster mechanism. And then at a certain point, I can just cut the tree, the dendrogram, and that would be my clusters. So to give an idea on how this actually works, let's consider where a scenario where we have three groups, the green one, the blue one, the red one. And the interesting point here is that each of those groups have a different number of antennas. So the green one would have 16, the blue one would have 4, and the red one would have 8. So what would happen if we start to compare the similarity between those two users? And again, assume that the channels are following that Gaussian distribution style. Not Gaussian distribution, regardless. If you start to compare the two groups according to the similarity that I just showed you, and you do multiple iterations of multiple realizations of these channels, you start to get something like a Gaussian distribution. So this Gaussian is basically the similarity of different realizations of these two guys, the blue and the green one. And what happened is that if you, okay, I'm looking for the wrong thing. So what happens is that we are interested on performing the asymptotic behavior of this Gaussian curve. And the reason for that is because if you start to do the same similarity, if you start to compute the same similarity for other curves, for other groups, so for instance, the blue and the red one, which are far away, you obtain that it behaves similarly on the same histogram or Gaussian distribution style. But if you assume that, maybe the illustration is not good, let's put it like this. So if you assume now that you are performing this comparison among the different groups, what you obtain is that the blue curves, these three, are representing the similarity of these users, and we are interested in computing the asymptotic function of asymptotic behavior of this blue curve if the users belong to the same distribution. So if R1 is equal to R2. And what we obtain is basically that if you consider this null hypothesis case, this case where the distributions are the same, you end up with a perfect match when that's true, and you end up with a mismatch when this is not the case. So basically you have that the histogram is on the left-hand side of the asymptotic or expected behavior. And we can use this as a hypothesis test or clustering mechanism style. And that's basically what we do. So we want, in two papers, we want to find this black curve. In GlobalCom, we obtain this black curve considering that we have the covariance matrix. And as ICASP, we just consider that this was estimated covariance matrix. So we obtain direct from the observation, from the channels. And the reason why, another reason why we want to have this curve is because if you normalize the similarity that we have with these two metrics, so basically the mean of the Gaussian curve and the standard deviation of the Gaussian curve, we obtain a Gaussian curve or a new similarity metric in the normalized metric space with mean 1 and standard deviation. Sorry, mean 0 and standard deviation 1, which is basically what is it again. And the nice thing about it is that we could use this information to perform this hypothesis test that I just showed you. So in short, well, after this whole thing that we do, what we did is some numerical validations. So here what we have in, maybe let me pick one of those, this one. What we have is basically that this curve here in blue is this comparison or the probability of successfully merging or successfully distinguishing one user of a different group with respect to the number of antennas. So for instance, the blue curve, what we have is in this point right here, is basically saying that I'm 100% sure that if I use this normalized metric, I'm able to merge the correct points in this specific scenario. And what basically we have in the 4 different plots is varying the number of antennas, which was a problem in our original setup. So if you have the number of antennas equal to 1, so the number of antennas equal among different users, I obtain a good behavior in the blue curve. And the yellow curve basically represents the case where I have an estimated covariance matrix, and the other ones basically represent a comparison metric. So the idea here, in short, of what it says, what we have here, is that in different scenarios, our two proposed methods you still overcome the generic things that are proposed in the literature, so the literature metric. And what we have in another result is basically that if I move apart two observations, I obtain a similar behavior. So basically, if I have two observations, three observations, two clusters that are very close by, I'm still able to perform a good clustering. And of course, as far as I move them apart, as long as I move them apart, the clustering becomes easier and easier. So I'm moving to the end. Basically, in short, what we have is that it's useful to perform clustering using this unbalanced scenario. Sorry, it's useful to perform hierarchical clustering in this unbalanced grouping scheme. Statistical analysis can give a good intuition of how to better measure a hypothesis testing. And we also perform a way to do clustering on complex subspace. So the literature, it's often the case that you only have real space or real subspace classification. And here we propose a new way to perform or to extend these works into complex subspace. So to recap and give a bit of a conclusion, we wanted to do clustering of users in the broadcast channels, and we did this using a hierarchical clustering scheme. Some random matrix theory applications were used to derive the asymptotics of the similarities in the Grassmannian manifolds. And some analytic studies were done for the kernel observations in the first example that we had. Here are some of our publications that we also have collaboration with Christian and Anai. And thank you. If you have any question, feel free.